All right, moving right along into section 16.6, path independence. So I have said that there's path independence for delta V, but now we're going to look at this in more detail. And we did show this actually with potential energy in chapter 6. So potential energy depends only on initial and final state, not the path. And so the same is also true with delta V. So same concept for potential difference. So delta V is equal to VB minus VA. So if we have A is here, B is here, it does not matter if we go a direct path or we just go all over the place. Delta V of each one of those is the same. Now, obviously you want to choose the easiest route when you're solving problems. This is easier to solve, and you'll get the same answer. So the trick is, how can I get the answer that I'm looking for the easiest way possible? I mean, we're all about making stuff easy. Okay, so let's do an example just to kind of conceptualize this point further. So just a quick note, always make your life easy. Okay. So let's say we have a capacitor and we're going to go from A to C. So C is at x1, y1, 0, and A is at 0, 0, 0, and we have an electric field in X, like so. Okay, so what is delta V from A to C? So delta V is equal to minus E sub x delta x plus E sub y delta y plus E sub z delta z. This is equal to minus E sub x, x1 minus 0 plus 0 plus 0. Okay, so we get that our potential difference is minus E sub x, x1. Easy. Well, let's take a different path to get there. So we could do A to B to C. So we're still going to look at the potential difference between A and C, but we're going to take a little pit stop off at position B, which is at x1, 0, 0. And everything else is the same. So there's two steps. VB minus VA is equal to minus E sub x delta x plus E sub y delta y plus E sub z delta z. This is equal to minus E sub x1 because this is 0 and that is 0. And from B to C, you could probably tell by looking at it, the path is perpendicular to the field, so it's going to be 0. But let's just show it. VC minus VB is equal to minus E sub x times 0 plus 0 plus 0. And so when you add the two of them together, delta V is equal to VC minus VA is equal to minus E sub x1. Path was irrelevant. It was the same all the way throughout. All right, so we can do a more complicated example. Maybe you say, oh, but Dr. Grace, you chose something easy. Okay, so Let's do a point charge problem. So if you recall that delta V point charge so VF minus VI is equal to 1 over 4 pi epsilon naught Q times 1 minus R2 minus 1 over R1. Q can be positive or negative. Okay, so if we have a point charge, let's say we have our field. Just make it a nice positive field. Put in some different radii. Okay, so let's look at our path. So we're going to go from our initial spot and to A. So R1, R2, to B, to C, and all the way down to our final position. All right, so we are taking this path around a point charge. So we know that all of these are going to be at 90-degree angles because it's radiating out in all directions. All right, so let's see what happens with these 3 spots. So what we're going to look at is delta V1, which is going to be VA minus VI, delta V2, which is going to be VB minus VA, delta V3, which is VC minus VB, delta V4, which is V final minus VC. So just going all around. Okay, so looking at the solutions, we have here that E is perpendicular to delta L, so delta V1 is equal to 0. So you can see that here, it's just going perpendicular, that's easy. Okay, for V2, that is A to B. So then we have delta V2 is equal to 1 over 4 pi epsilon naught Q times 1 over R3 minus 1 over R1. Then we have V3. So once again, we have that our electric field is perpendicular to delta L. So delta V3 is equal to 0. And V4, delta V4 is equal to 1 over 4 pi epsilon naught Q times 1 over R2 minus 1 over R3. And so V final minus V initial is equal to delta V1 plus delta V2 plus delta V3 plus delta V4. So this is equal to 0 for the first term plus 1 over 4 pi epsilon naught Q 1 over R3 minus 1 over R1 plus 0 plus 1 over 4 pi epsilon naught times Q 1 over R2 minus 1 over R1. And we see we've got, oops, that's supposed to be an R3. So we see we've got a positive R3 here and a negative R3 here, so those terms will go away, and we're left 1 over 4 pi epsilon naught Q times 1 over R2 minus 1 over R1. Oh my goodness, this is exactly what we calculated. My word, physics works. I know, incredible. Okay, so a couple more notes on path independence. So delta V, due to a stationary charge, is independent of path. Delta V of a round trip is 0. If you end where you start, you haven't really gone any distance. And delta V is always independent of the path taken between two locations. And on your own, prove that delta V is equal to 0 is a product of the energy principle. All right, so there are a couple important applications. And we're going to go back to conductors. All right, so when you're polarizing a conductor, for a brief time, E net is not 0 because those electrons do actually have to move. And during that time, they're going to have a non-zero drift speed. All right, so if you want to keep the electrons moving, let's say you have a circuit. So electric circuits utilize a battery to maintain a non-zero field. So basically a circuit works by saying, hey metal, I'm going to run a field over you and you're going to move your electrons and try to polarize. Oh, just kidding, can't polarize. Oh, just kidding again, still can't polarize. Got to keep those electrons moving. That's basically the immature way of thinking about a circuit. So basically you've got a continual polarization process with no equilibrium. And so the electric field pushes the mobile sea of electrons through the wire. All right, so let's bring that into potential. So in a wire, the potential difference is minus E times L. So you've got E that's pushing those electrons through, and L is equal to wire length. So, and we're going to definitely build on this concept more, and so circuitry is a part of standardized tests, and what we're going to do in this class is more than just memorize the formulas. We're going to understand the physics behind whence they came. All right, so cool concepts. Some electric field patterns are impossible. So, for example, Could this be made with point charges? And the answer to that is no. Remember, point charges do this or this. So we have an impossible field for point charges. There are no curly fields for point charges. So no curly fields for stationary charges. All right, that wraps up 13.6. Or, my goodness, 16.6.